So, what we're going to be talking about today. I'm going to go over a brief overview of the PS5 security model. I have given a talk about this previously at hardwear.io USA last year. So I'm not going to go too in depth on it, but I do want to cover what the hypervisor is and why it matters that we're breaking it. Then I'm going to talk a little bit about the current state of PS5 console hacking, some of the current bypasses and techniques that are used, and what's changed recently that has allowed more research. So after that, we'll get into an analysis of two vulnerabilities in the hypervisor, which will result in the first full hypervisor break that's been published. And we'll wrap it up with future research and conclusions. So, a few quick notes before getting started. The focus here will pretty much be entirely on the x86 kernel and hypervisor. So all the other like security coprocessors and whatnot aren't going to be talked about. And the hypervisor break is for, it says 2.50 and lower, but technically it's 2.70 and lower. So yeah, the code and tools will also be published at some point after the talk. Not sure exactly when, but I'll try to do it within a couple days. When it does go up, it will be under the PS5 dev organization on GitHub. All right. So yeah, as I said, I gave a talk on the PS5 security before. The slide I have up is a bit of a TLDR on it. So the PS4 was a little bit of a joke security-wise. It had some of the mitigations that you would really hope to expect, like no execute and ASLR for the most part. But it didn't have more modern mitigations like supervisor mode access or execution prevention, and it didn't have execute-only memory. The PS5 has all of these things. So Sony loves their security through obscurity, and so they worked with AMD on a hardware-enforced execute-only memory. So if you come from ARM world, you may be a little bit familiar with this. I believe this was pioneered by ARM. But so in most systems, if you can execute code, it's implied that you can read it. But if execute-only memory is in play, that's not the case because the CPU will not allow data fetches to executable pages if the XO bit is set. It'll just throw a fault and won't read it. So this executable memory is used in both user space and the kernel. So it's used in games and applications and system libraries, and also on the kernel text. And the mitigation is enforced by the next level up. So userland executable memory is enforced by the kernel. Kernel is enforced by the hypervisor. So yeah, if you have kernel read-write, disabling userland executable memory is as simple as just iterating the page table entries, flipping the exotext bit, and flushing page tables. And the code that I have up here is kind of demonstrating that. But in the kernel, it's a lot harder to break because the system uses nested paging, which is provided by AMD's virtualization. So if you go and flip the execute-only bit on the kernel's PTEs, it's just not really going to do anything because the ultimate authority on the PTE, like the page permissions, is going to be the hypervisor's nested tables. So again, a diagram I ripped from my previous presentation. So it's just kind of showing, like if you're the CPU, you try to read kernel text, it's going to go through SLAT. And when the CPU sees the XO bit in the PTE, or more accurately, the TLB entry, it's going to throw a nested page fault. Of course, the integrity of the kernel text pages is also protected. They're not supposed to be writable. We'll kind of get into that in a little bit, I guess. And the write protection is enforced through control registers. And the hypervisor intercepts writes and reads to sensitive control registers and machine state registers. It'll either filter your bits, so it'll just filter out any security sensitive bits, or it will just refuse to commit the changes and inject a fault in the guess. So what does execute-only memory mean? What are the implications? So it makes getting gadgets difficult for doing kernel ROP if you want to do code execution, although it is possible, as we'll get into in a little bit. But the main thing is that the reverse engineering efforts are pretty significantly hindered for most people. Until now. So yeah, there has been some workarounds for the later versions of the hypervisor. So the 3.x to 4.x firmwares have had a public kernel exploit for a while now. The hypervisor is stronger on these higher firmwares, but some tricks have been discovered over time. Because the hypervisor can't intercept everything, the kernel needs to have some autonomy to do what it needs to do, and you kind of have a catch-22 where the more that you move into the hypervisor to try to secure it, the more you're increasing the attack surface, so it's trade-offs. These tricks don't result in a full hypervisor break, but they're still very useful in their own way. So one that I had worked on was talking to devices via memory-mapped.io. So the kernel, most devices, the kernel can talk to directly. There's only a few that the hypervisor reserves for itself, such as the IOMMU. But yeah, the platform security processor, which is involved for a lot of decryption and whatnot, the kernel can talk to directly. So I wrote something that would send and receive messages directly to the platform security processor with just a kernel read-write primitive. I didn't have time to put this into practice for my last talk, but since then, I've been able to use this to decrypt system libraries. So a large reason I was able to do this was because of a kernel dump kindly provided by Flats. So I was able to reverse the relevant functions and message structure. So that SBL service mailbox call is used for pretty much every message that goes across to the security processor. And then by xrefing that, you can see all the different APIs. The auth MGR one is the most relevant for decrypting system libraries. And then the driver send message function actually does the MMIO. So by reversing all these things, I was able to basically emulate these functions. So yeah, I could send decrypt requests directly to the PSP and profit. Some of you who look at x86 a lot probably recognize some opcodes in the bottom half there. And yeah, so that's basically just showing a response from the PSP and decrypted segment data. This could also be used to decrypt games, which partially breaks Sony's security model. Obviously they don't really want you to be able to do that. But I mostly use this to decrypt system libraries. This trick is great for poking around. It can pretty easily be ported to other system versions, even if you don't have the kernel text, because you only need a few offsets that are in the data section, and it's only really for resolving physical addresses. So there's patterns and stuff that you can pretty easily find these values. But this does have some limitations. Making this useful for homebrew would be a little bit painful, I think. You would basically have to man in the middle the mailbox and rewrite requests and responses. I think it would be doable, but it's a little bit painful. And this can't be used to decrypt the kernel or the hypervisor. The PSP seems to lock out decryption of these files sometime after boot. Another method that's been used is IDT hijacking. So this can be done to do a sort of soft hooking on the kernel. So IDT, interrupt descriptor table. The idea here is you can set up your own custom gate entry and then point the interrupt stack to a ROP chain that you control. And then you take a pointer that is dereferenced by the code that you want to modify the control flow of and poison it. So you change the upper 16 bits to some garbage to make it non-canonical. And then when that faults, it will follow your fault handler, and you can hook that way. So diagram kind of showing this. So the CPU, it's dereferencing this kernel pointer. We change the upper bits to DEB7. It doesn't have to be that. It can be anything. That's going to throw a GP exception when that pointer is dereferenced, goes into the IDT, follows your ROP chain, and you have hooking. So this allows PS4 Homebrew to run on the PS5. It also allows some limited introspection and debugging. You could use this to single step and find kernel gadgets, and do a little bit of debugging. But again, this has limitations. The main one being that this can really slow down system performance, because you're essentially causing a crash every time a pointer is being dereferenced. So if that's code that's called into a lot, that's going to add up. You can get to like 100 times slowdown in some areas. And the setup to do this is a little bit painful because you still need some initial gadgets to get started. So it's a little bit painful on versions you don't have any information for. And again, this doesn't defeat executable memory in the kernel, so it doesn't allow kernel reversing. So recently, A vulnerability in user mutexes, or UMTX, was disclosed in FreeBSD by Synactive, which opened up the firmware version range that's exploitable to 1.x to 7.x. And exploit code published by Fail Overflow and Flats allowed some rapid exploitation of the bug. So big thanks to them. Without their work, I doubt this presentation would have happened today. So yeah, it opens up higher firmwares, but for me, what I mostly cared about was lower firmwares, because it allowed me to test out some theoretical bugs that we had, but just weren't able to test and actually confirm. And we were able to stumble on a new bug that's quite a big fail. It's pretty funny. So let's get into them. So the Hypervisor went through a bit of an interesting development process. So I have a timeline here of 3 versions that I would consider significant. So there's obviously the initial release version, which is pretty bad, and is the one we're going to break. It has the Hypervisor embedded inside of the kernel. And then in 3.0 firmware, they moved the Hypervisor to its own separately loaded component. So it was a pretty major overhaul, so I call this V2. And then we recently found that the 5.0 firmware, again, introduces some leaps in its security. And a lot of the, like, even private hypervisor exploits that work on 3.x don't work past 4.x. So some of you probably spotted the problem that we're going to be abusing here mostly, and that is the fact that the hypervisor is embedded in the kernel. This is a pretty big red flag, because isolating hypervisor data from the guest is pretty difficult with this design. They tried. So the hypervisor does have its own exclusive region for security sensitive things that are unmapped from the guest. So it'll use that area for storing like the hypervisor's page tables, the nested page tables, VM control blocks, MSR protection map, IOMMU tables, pretty much anything that you could imagine that they would not want you to have access to for breaking x86 entirely, they try to put in this section. The problem is the code and the static data that it relies on is still accessible to the guest, particularly the jump tables. So the jump tables used by hypervisor code is mapped in the guest page tables. 2 of them are particularly relevant for us. Both of them are in the VM exit handler. So one jump table is used for switching on the exit code. The other one is used for switching on the VMM call, which is the one we're going to target ultimately. So, you know, they tried, but it wasn't enough. So these jump tables are in read-only pages. But we can gain write access to them via a technique that I call mirroring. So the idea here is, in user space, we request a read-write mapping from the kernel through the mmap system call, and then we use the kernel read-write to iterate the page table entries and just change the PTE address to a kernel page. I think they might have had a bug in their nested page table construction or something, because I don't think this should work, but it does. So we can use this to get write access. So the idea here is we overwrite the jump table offset for some entry, and we get code execution in the hypervisor. So sounds great. Exploiting this, though, is a little bit more challenging than it seems at first blush. Because, well, can we shellcode? Well, not really, because the hypervisor page tables are only going to have the kernel text mapped as executable. So, and obviously, as we covered already, you can't write there. So we're going to have to ROP. ROP at first seemed a little bit difficult because we have almost no control over the registers that the hypervisor uses. It's going to initialize them with its own values, and 1 or 2 of them we have very, very limited control over, but not enough to kickstart a chain. But what was a little bit surprising is that the registers that the hypervisor doesn't initialize are preserved across the VM exit boundary. So if you set up a ROP chain and invoke a hypercall or something to enter hypervisor code, any registers that it doesn't overwrite are still going to contain the guest values. So yeah, we can set those up in a ROP chain. So we're essentially going to have 2 ROP chains with this exploit. One is going to be for setting up the registers and invoking the hypercall. The other is going to be for the hypervisor to run it and break itself. So yeah, this is kind of showing that. So this is the jump table for the VMM calls. So we take the set CPU ID PS4 hypercalls entry, It was a little bit arbitrary, but it's a nice hypercall to choose because this hypercall is used for emulating PS4 games. So as long as you're not trying to launch like a PS4 application while you're running the hypervisor exploit, you shouldn't run into any weird races with like trying to run the hypercall while the entry is being changed. So yeah, we cross out its original contents, put an offset to a job gadget there. And this is what our register context kind of looks like at the time we get the code execution. So I have the disassembly there, but the Cliff's notes are on the right. So the registers we really care about are the R14 register, which points to this virtual CPU object. And then at offset hex 8, field hex 8 in the virtual CPU object, we have a VM control block, which is going to be very nice to target. RCX holds the jump table that we're hijacking, and then most other registers we don't really have control of. So to get control of registers, we use set jump and long jump gadgets. But this puts us in a bit of a chicken and egg problem because you're trying to get control over registers before you have control over any registers. So the solution to that is job. So we run a jump-oriented programming chain, jump to set jump and long jump using the limited control we have, and then we stack pivot. We also have control over RSI and R9 from the guest kernel, which is going to be relevant for the gadgets we use. And it's worth noting, too, that we control any contents in the kernel data range. So any like RIP relative instructions are also fair game for gadgets. So this is ultimately what our job chain looks like. So in green, I have highlighted the controlled register from guest. Blue is the jump table. So the first gadget that we run basically just loads RDI with a pointer we control, and jumps to a second gadget, which will invoke set jump, which backs up the registers to a like scratch area, and then we invoke long jump after modifying the registers. So that reloads them, and then it will also let us control RSP and stack pivot. So at this point, we're executing in hypervisor context, and we can use the existing register context from the hypervisor's VM exit handler to access the VM control block. Again, that's through our memory at R14 plus 8. So the VMCB is pretty important because it contains the flags that enforce the hypervisor guest security boundary, particularly this hex 90 field. So I have a screenshot here from the AMD programmer manual. But the ones at the top are the most important. So you can see like the nested paging enable flag is there, SEV, although we don't really care about that, and guest mode execute trap. So by just writing a 0 to this field, we can turn all these things off, and we win essentially when that happens. So this is showing the hypervisor ROP chain. Nothing too crazy. It's a little bit long because we had to get creative with gadgets. But yeah, it basically writes a 0 keyword to the hex 90 field to turn off nested paging and GMET. But we still need a ROP chain to set this all up and trigger it. So for nice ROP chains that don't violate CFI, although CFI isn't really a problem, we can turn it off pretty easily on lower firmwares. But even still, we want a nice ROP framework. So I took a bit of inspiration from the user mutex chain that Failoverflow and Flats had worked on. So I basically use threads. So I create a thread in user space, make it do some blocking read operation on like a pipe, and then on another thread, I use the kernel read-write primitive to iterate the processes, iterate its threads, find the kernel stack, and then edit a return address on it. And then whenever I want to trigger that chain, I can just write to the pipe and unblock that other thread. So it's very clean. You don't really need any fix-up. So that's what that part looks like. Again, nothing crazy. It's just setting registers and invoking the set CPU ID hypercall and then returning cleanly. So after this chain completes, the VMCB on that core has nested paging disabled. So we're free to edit kernel PTEs. We can disable execute-only memory and enable the write flag. So the hypervisor and kernel integrity is pretty much entirely broken. And it's only broken on that core, but we can use that core to edit the VMCBs of all the other cores and turn them off there too. So it's, if you wanted to do that, it's not a big problem. So this is a POC, kind of showing it off. So again, if you're an x86 guru, you probably spot the opcodes like the UH, OA, VATS, whatever, prolog. But yeah, this is dumping the sys get ppid system call code. So execute-only memory is turned off. So this is really cool, but it's not ideal because the ROP chain is pretty complex and it requires a number of gadgets. Porting these to a firmware that we don't have kernel.txt knowledge for would be very painful. And your debugging capability is pretty limited. The only debugging capability you really have is using infinite loop, like known infinite loop gadgets in your chain and using that to like single step if you have any problems. Like I said, it's doable, but it's painful and a lot of work. Thankfully, there's another bug. So, Chendo Chat noticed this when I was in the process of porting the first exploit to some other firmwares, and noticed a condition in the hypervisor's nested page table construction. So they invoke this SERCMGR QAF SL debugger enabled function. Basically what that's doing is checking if the system level debugging flag is set in the QA flags. If it is, it's not going to set the execute-only memory bit on the kernel text pages in the nested page tables. But if that wasn't good enough, it also makes them writable. So this is clearly some debugging functionality that was left in. So that's kind of showing the PTE construction code, just showing like, yeah, it's read write and no exo text. And these flags are shared with the guest kernel. We actually set this flag already without realizing all the implications in the existing kernel exploit chains, just because it is kind of useful for getting more verbose logs and whatnot. At first glance, you're like, okay, these flags are shared and they can enable this condition, but this is in the hypervisor init code. So, we're getting code execution, or kernel read write way after the hypervisor is initialized. So it seemed like maybe one of those bugs where it is a problem, but it's not really a big problem. But what happens if we enter a sleep state boot path? Well, on suspend and resume, these flags are just copied back over from the hibernation file. The QA flags aren't reinitialized by the secure loader, but the hypervisor gets reinitialized. So we can basically exploit this by doing almost no additional work. We just run the existing kernel exploit chain we have, put the system into rest mode, turn it back on, and then we can modify the kernel page table entries to remove the XOM bit, make everything writable, and we're not going to clash with the nested paging permissions anymore. So we win. Yeah. So this is pretty much the exploit code in its entirety. So this allows full break of hypervisor and kernel integrity again. But this time, only a few offsets are needed. So on the left, I have all the offsets I needed for the first bug. There's like 27 of them there. Now we need 5. And again, they're pretty much all just used for resolving physical addresses, so they're not particularly hard to find either. Flat's also published another bug. So I have his tweet here. I wanted to show it because it kind of reinforces the point that I'm going to make. So he says, there are a few ways on PS5 to defeat the hypervisor. One of the methods that I found was related to APIC, or Advanced Programmable Interrupt Controller. The APIC ops structure is located in the read-write segment of kernel data. With kernel read-write, you can overwrite a function pointer inside it like xAPIC mode and get ROP. And you can get code execution before the hypervisor even runs. So this is just kind of emphasizing that, like, if you're like, their order's kind of backwards. If you have the hypervisor embedded in the kernel and the kernel is responsible for initializing it, all you need to do is get code execution early enough in the kernel, which is possible when you abuse sleep states. So I do have a live demo set up, and if the demo gods are with us, hopefully it works. I do have a video backup if needed, but again, hopefully I don't need it. So let's see if we can get that working. Oh, not off to a great start. Let's see if I can set up the capture card to get it. This is the one thing I was worried about, was the capture card. Okay. I was expecting more trouble. That's very nice. We're not out of the woods yet. Okay. So I'm going to launch the... I'm going to unplug that for now. So I'm going to launch the userland hypervisor, or sorry, kernel chain. This is pretty reliable, so if this part fails, I'm going to be very sad. Okay. So... So now we just go to the system. Let me close or minimize my terminals here for a second. So now I just need to wait a minute for rest mode to complete, and then I can resume. And when we resume, because the elf loader that's out there persists across sleep mode, I can just send the payload again, and we should be good to go. The payload isn't finalized yet for this hypervisor exploit. I would like to make it so that you only have to send it once. It would be a lot more, straightforward. But even getting this demo to work as it was very much a last-minute thing. So, okay. Okay. So we're just going to send the same payload again. So what this payload is doing is it's patching and installing hooks in the kernel to be able to run Homebrew. So I'm going to switch back over, and we should be able to install a Homebrew application and run it. There we go. So Teamstar said that this would be a little too boring. He was ripping me out for saying, you spent all this work to render a PNG. So the last hour or two, I've been making it better. I've now made it a PNG that shoots lasers when I hit the trigger buttons. Okay. We don't need that anymore. Perfect. So conclusions. So the ability to read-write kernel text pages gives us a lot of opportunity for research. Instead of just kind of blindly poking with kernel read-write, we can now actually leverage built-in kernel API to do things and reverse how devices work. We can look into the interfaces a bit more. And we can also patch and hook to gain additional introspection. Debugging future kernel exploits is also significantly easier for the same reason. We basically end up in the same situation the PS4 was in after kernel exploit. So booting Linux should be possible. It would be a lot of work, as has been shown with the PS4, but it should be doable. So yeah, this lower version hypervisor is a pretty flimsy implementation. When you have the hypervisor integrated with the kernel in this way, separation is pretty much impossible. And Sony realized this, to be fair, so that's why in 3.0, they redesigned it so that it's loaded separately and these exploits don't work. Breaking the hypervisor on 3.x Plus is more challenging, but it has been done. And while 2.x firmware is a little bit old at this point, these exploits still allow public researching into the system that wasn't really possible. And this can be used to find bugs in other coprocessors that could be very useful as well. So if you found this interesting, I would recommend checking out Sean Hoffman or Shuffle2's presentation. He gave a presentation looking at Titania and Selena SoCs. So this is mainly for like their custom SSD controller stuff. They have a lot of weird stuff going on there. But that can enable even more research into like some of the other auxiliary processors. So yeah, final word. Again, the repo will be published soon after this talk. It will include code to dump the kernel in its entirety, as well as some example patches and hooks to load Homebrew. Analysis scripts and loaders will also be included. If you're interested in doing PS5 research and this presentation got you inspired or something, I have a Discord that I run for that. The link is there on the slide. And if you want to reach out to me personally, I have the handles SpecterDev on Discord and Twitter. I would like to shout out a few people. As I said at the beginning, console work these days is very much a collaborative effort. It's way too monolithic of a task for one person for the most part. So Chendo Chap was a big help. He did a lot of the work for trying to find the gadgets for the ROP chain and spotted that meme bug and helped a lot with getting the demo working too. We had a lot of fun with that. Crypto issues and bugs, very fun. Flats also enabled a lot of the research with the kernel dumps, and he's just a wealth of knowledge in general. Fail Overflow, again, they allowed the kernel exploit to like test out these ideas and stuff. And there are a few others like KiwiDog, Teamstar here, and some other people at Hardpwn that helped me out with getting this all set up and this cable monstrosity wheeled in here. So big thanks to everybody involved in that too. And yeah, thanks to Hardware.io for letting me speak. And that's all I have. So thank you.
Thank you for the talk. Very nice demo with the shooting laser beams. Are there any questions? We have time for a few questions.
Okay.
I think there's no questions.
Okay. Fair enough.
Fair enough. Well, then let's thank the speaker again.